Very, very exciting work, yes. All right, let's see here. I think that should do it. All right, I will... Oh, you missed it.
I saw. Did I see what I forgot? We started cooking in the year 2008, right after we finished his PhD.
No, it was just now. He just did one.
Oh wow.
Strange and looks exactly the same, but up
All right,
Yes, you saw it.
Oh, you can have more time if you need it, but had enough? Okay, good. I understand, yes. All right, I will begin with a word of prayer. Sometime soon. Dear Father, we thank you for this day. Again, I thank you for this class. I just ask you to bless our work today, Lord. Help us to glorify you in what we do and just understand a little more about your creation. In your name I pray, Lord Jesus. Amen. All right, so I will try to go over a little bit more about the Frobenius Theorem. If I can find the first page of my notes, that'd be helpful. Did you take them? No. Okay. Well, I said if I could find the first page of my notes, it'd be helpful, and then you went like that. So it made me, I thought, maybe, but no, okay, good. All right, so I started talking about stating the Frobenius theorem in terms of differential forms last time. So I want to try to talk more about that today. And hopefully I'll have an example and hopefully we'll make sense of it. But so basically we're studying a distribution. And I'll try to stick with the notation of last time. We used a triangle for it, right? Yep. It was, and so the way to, one way you could say is it's a subset of Tm. Now this Tm is the tangent bundle. Don't make me define it carefully, but the tangent bundle is technically the collection of all tangent spaces. So to say that a distribution is a subset of the tangent bundle is just a fancy way of saying it's a collection of tangent vectors, but for manifold. The manifold. So, all right, and so, essentially, the idea was that if we look at the bracket of vector fields that are in the distribution, if they're again in the distribution, then this makes the distribution, what we said, involutive. Now, there is like a local lemma. If we have, if x1, x2, xk are smooth local sections of the triangle. Now that's just okay, so what's a section? A section is, what that means is it's a function that takes its values in the bundle. So like actually this distribution would I think technically be a subbundle. And to say a section of a subbundle is just a fancy way of saying a function that takes its values in the, well anyway, this is just a fancy way of saying these are smooth local vector fields that fall in the distribution, all right? By this I really just mean that nabla Q is the span of, x1 at Q, xk at Q, for all Q in some open subset of the manifold. All right? So you can build the distribution from the span of these local defining vector fields. All right, that's what we mean by, well, that's what we mean by locally representing vector fields of the distribution. I mean, this is kind of silly in some sense, this, the care I'm taking at the moment, because pretty much every example, I think literally every example I'm going to show you guys, there is a global, there's a globally defining set of vector fields for the distribution. So like I just have a vector field in the span of the vector field, and that describes the whole distribution. But in principle, you could have different vector fields in different spots, and they could do the weave and put them together, make it more intelligent, you know. You'll have to be really intelligent to do the weave, I've heard. It's documented in the podcast of our time. But let's see here. So, oh yes. And you know, x sub I, x sub j, the Lie bracket of that is an element of, well, let me just say at the point Q is an element of the distribution at Q, all right, for all I and j that range from 1 all the way to k. If you have that condition, that suffices to give you that it's involutive. Right? So you don't have to check the closure of the brackets on a span. It's enough to check the closure of the brackets on the basis for the distribution, basically. Although perhaps I shouldn't use basis. The reason I shouldn't maybe use basis is it's not a vector space. It's like a module. Because we're thinking about vector fields, and so the coefficients really aren't scalars; they're smooth functions. So that's what's it's called a module structure, which is like a vector space, except instead of the scalars being a field, they're a ring, the ring of smooth functions. Anyway, so that is a sufficient criteria to get the involutive condition, and then the Frobenius theorem said that if the distribution is involutive, right, then that implies that there exist these integral submanifolds, right? Basically that we can integrate and find these essentially we can integrate the vector fields and find the integral curves underlying those, and then we can somehow paste those together to make these submanifolds, which then foliate the plane. They foliate the manifold, right? They actually fill out the manifold. Now, but I started talking about the dual description of this, right? The dual description of this in terms of one forms, right? And so I should talk more about that. And this will be a few lemmas to put us together here. I would say, roughly speaking, Frobenius theorem, just to write it down, said delta involutive if and only if the tangent space to some submanifold. I mean, this is very this is a little bit sketchy. But what I'm trying to say,
Wasn't it completely involved or looking slightly different than completely involved? It was completely integrable. Completely integrable? If and only if
this over here. Oh.
Oh, it's back. You didn't
All right, just
I
a
understand now.
blarg. I said blarg.
Oh.
This is a civilized place. Come on. We can talk about it. People. You people. All right. All right. Fine. You've driven me back to write it out again. Theorem. Put it up here. Theorem. The distribution is completely integrable if and only if is involutive. But there was more than that. Yeah. Then the theorem, then a little bit later, we had the theorem which said that if the distribution is involutive, right, then the integral submanifolds of the distribution foliate M. All right. And that, I mean, I suppose you might take the latter theorem to be the Frobenius theorem. I don't know. This all kind of, to my mind, all kind of goes together to be the Frobenius theorem. But oh, okay. What's foliate mean? Oh, glad you asked. Let's look at some examples of that. Yeah. So there are some easy examples, and there are some not so easy examples of that. I happen to have a list. So let's talk about it. Example A, you can have collection of all k-dimensional affine subspaces of Rn parallel to R sub k Cartesian product with 0. This gives us a k-dimensional foliation of Rn. Let me make this a little bit less mysterious. Let's see here. So they're parallel to RK0. That would be like, let's see here. So I guess this would be up here. I would have x k plus 1. Oh, but well, that we did that last time. This time we'll do lines. So k plus 1 all the way up to n, and then over here I've got the coordinates, x1, x2, all the way out to k, right? So in other words, there's essentially a copy of Rk this way, and there's a copy of Rn minus k that way, right? And so this thing is just this right here, all right? And then it's the collection of all k-dimensional affine subspaces, so like we're talking about. You might think I'm trying to run out the clock today. That might be true. Yes.
Is that 0 and minus k dimension?
Yeah, that's a 0 vector. So that's a foliation, right? Because basically Rn, if you take any particular point in Rn, right? That point lies on one of these affine subspaces and only one. right? That's what makes it like a foliation. Of course, the simplest thing, even simpler than this, you could talk about, just R2 and take any line you like, and then take all lines parallel to that. That gives you a foliation, right? Take R3, take any plane that you like, take all planes parallel to that plane, that gives you a foliation, right? Those could be tilted. Like this one is very boring. It's just stacked with respect to the coordinate axes. This one's nice in the sense that we can write down equations for this one, right? Like, what are the equations for this is my typical sigma. I could label sigma by a point. I could label it by like C k plus 1 all the way out to what? Cn, right? If those coordinates, right? Essentially, this point right here uniquely defines that leaf, right? That particular integral submanifold, if we want to think of it that way, that point right there would be 0 all the way on out, and then ck plus 1, Cn, right? In other words, if I wanted to pick on that very particular leaf right there in the foliation, right, this one, the equations which define that are what? Zj equal to Cj for all j equals to k plus 1 to n, right? And as a submanifold, what are the, there's a natural chart. The chart is kind of dumb, right? Like we could use x1 out to xk, this restricted to sigma, let's call it C vector. That would give me a k-dimensional chart on this k-dimensional space. But in this particular context, I can just, bogart the chart from Rn, But yeah, that's what the complete integrability says, is that given a manifold, it's possible to choose coordinates on the manifold for a k-dimensional involutive distribution such that the integral submanifolds look like this with respect to the manifold chart, at least locally. Maybe not globally, but locally you can do this. Yeah. Okay. What would the distribution, what distribution would take these as the integral submanifolds? That's probably an easy, good thing for us to figure out right now. What would the triangle be here? That would give me that as the leaves in the foliation. What those integral submanifolds are tangent to what? Yeah? Span of what? Coordinate, yeah. Partial x. Partial.
Velcro, man.
What? What was that? That's like way worse than sharpening your pencil in class. Let's see here. The only way to get past this is to open up a bag of chips and start what? Oh, those are.
There's some right here.
Hey, those are mine.
Man, all right. I equals 1 to k, I think, maybe. Am I wrong? So those coordinate partials, right? If you find the flow of those, right? Like the flow along any of these vector fields, what happens is we're just talking about the coordinate lines. What is it? So alpha of x comma t, it's just going to be like the ith one. What's going to happen is you're just going to have x1, x2, and then the ith one, like that. that's how you'd flow along the I coordinate derivative. This curve, if you differentiate it with respect to t, gives you back that at any point, if you put t equal to 0. Anyway, doesn't matter. Like, you guys can ignore that if you want. I don't really want to get into it. But do you guys agree that like these take those as their integral submanifolds? Do you understand why I'm saying that? No? No. Think I'm wrong? You don't understand. Okay. Well, so let's see here. If I have a curve, gamma of t, right? And it lies in one of those integral submanifolds, what would it look like? It would have the last, let's see here, the last or the first? It has the, yeah, it has the last n minus k things frozen, right? So you got like gamma 1, gamma k of t, right? These could all vary, right? But if this curve lies in the integral submanifold, then this over here is fixed at c, right? This is a curve in the in this one, yeah. Now the first k components can be completely arbitrary. What happens when I differentiate this? Like, what's gamma prime? Let me write this instead. Well, okay, fine. So like gamma prime of t, it's the sum I equals 1 to k of the derivative of well, let me just get to the point here. Gamma upper I dt, right? Partial xi at gamma of t. And that is an element of the distribution at gamma of t. Which incidentally is, well, anyway, what am I trying? So I'm just trying to say, like, if I take a curve that's in that integral, that submanifold, and I differentiate it, the derivative is built from exactly what it should be, namely the tangent vectors that are allegedly forming the tangent space to the integral curve, namely the coordinate derivations from 1 to k. Anyway, let me go on here. So there are other examples of foliations. Don't let me erase this. I need to add to this. Let's see here. Example, what am I? I guess I'm using A. B, if we had m equal to like Rn with the with 0 deleted, you could look at that all rays from origin. Right? So like in 2 dimensions I can picture it. Right? All and on, right? There is a unique ray that goes through each point, right? And they fill the whole punctured plane. That gives you a foliation. All right? The open rays. Similarly, and perhaps more interestingly, if we take, say, Rn plus 1 and delete 0 from it, right? And actually, I don't think we even need to delete 0. Well, okay, fine. Yeah, we'll delete 0 from it. Oh, yes. Okay, I just remembered why deleting 0 is important. Okay, so like the two-dimensional picture, we can use all n spheres centered at the origin. So obviously different radii, right? So like we're missing the origin, and then I'll give you pictures of the n spheres. Are you ready? Sorry, I was trying to draw an n sphere, but they started getting lumpy. But you get the idea, I hope. I mean, of course, in the plane, in R2, we have S1, right? The unit circle, but we can also like contract it or expand it past, right? Circles of radius epsilon out to radius however much you like, right? There's obviously, for every point in the punctured plane, there's one and only one circle that goes through it, right? So, okay, so all of a sudden the question, okay, well, these are obviously foliations. It now becomes a somewhat more interesting question. What is the distribution which these appear as integral submanifolds for? Yeah, that starts to be an interesting question, which I'm not going to answer. All right, next one. Not with our current technology anyway. I might come back to this one and answer that question from the other formalism. This is sort of a meta example, but if we have M and N smooth connected manifolds, then M cross Q, as Q ranges over N, gives us a foliation of M cross N. An interesting application of this would maybe be the torus, right? Like we could picture the torus. Something like that, whatever. So the torus is S1 cross S1. Now, this is a somewhat heuristic picture, all right? Because it's a subset of a four-dimensional space as I'm currently defining it, yeah? Because S1 is a subset of R2. What's that? Heuristic? Oh. I don't know how to define that. But, so, essentially my point in here is that if you know, this can be the line of, like, for the sake of my artistry, well, I don't know, theta equal to, I don't know. What do I want to do? Theta equal to pi over 2. All right. And then, like, theta is equal to pi over 2 everywhere here. But theta, I'm saying, is measured in this way. All right. So, like, so my picture doesn't, that's the pi over 2. Like, theta equals to 0 is down here. So, like, the theta equals to 0 line is on the inside, yeah, of the torus, right? All right, so then on the other hand, it's sweeping around sweeping around, we're talking about beta changing, all right? So maybe, I don't know, I can't decide. I'll put, well, beta's got to be 0 somewhere, so, good grief. I don't know. I should have decided this before I taught today. I can't make my mind up. Beta equals 0 here. All right. So what I'm trying to tell you is we can foliate the torus, right, by taking the union of all these circles, all the way around. That gives us a foliation of the torus of that type. Because it's like we just got like, fixing the one, we're fixing one of these and just letting the other, fixing maybe the second one, I guess. Yeah.
So every parameterization is a foliation of some.
Possibly. Is every parameterization a foliation? I guess that depends on, the parameterization's got to be injective, right? If it doubled back, we'd be in trouble. But yeah, so that's a foliation. The one that's kind of more interesting.
Would the parameterization maybe have to be a coordinate map?
Yeah, maybe. So that was DE. He gives this. He gives gamma sub theta of t is equal to e to the it, and then e to the I alpha t plus theta. He says as theta ranges over R, it forms a one-dimensional foliation of the torus. So he says if alpha is in the rationals, each leaf is embedded circle. In other words, if alpha is rational, what happens with this map is it eventually comes back where it started and like closes back on itself. All right. On the other hand, if alpha is not rational, then each leaf is dense. This I cannot draw pictures of, but I will show you. Well, I don't know if he has a picture here. Oh, man. Oh. Well. Oh, I guess C is his picture of the dense case. So I'm currently in chapter 19 of John Lee's manifold book, if you're wondering. But we're skipping the harder parts. I'm just finding the easy things to tell you guys. So in this picture, like this is the one that we did to start with, the nice Cartesian product one, just vertical circles. I think B is what happens if alpha is rational, like it just comes back again. But if alpha is irrational, it just keeps going and going and going. It never gets back where it started, and it will cover the torus densely. Like it just keeps winding around and covers any point you pick on the torus. You can go far enough in the densely wound leaf that it will get as close as you like to the point that you just picked. In the same way that like rational numbers are dense in the real line. That kind of dense. So, yeah. Anyway, those are some examples of foliations. You can also have more, Calc 3 kind of things. Like, how about this? If we have x squared plus y squared, over 2, z squared over 4 equals to a constant, this gives me a foliation. This describes a foliation of R3, right? Into ellipsoids, right? As long as well, okay, I should be careful. What's the problem here? And it was the same problem, actually, I forgot to talk about for part C. What would happen if I mean, sometimes I would say, oh, it foliates the whole of Rn, right? I just allow the case that a sphere of radius 0 is the origin. Well, that breaks down our larger discussion here, see, because the integral submanifolds have to have a certain dimension, which is not 0. Right? So that would be breaking from our larger discussion of all of the integral submanifolds having the same dimension. Right? So to avoid that, that's why we can't have 0 and have it part of this discussion. Likewise here, I can't have 0, I can't have c equal to 0, which of course the solution to that is just the origin, because that wouldn't be a surface. That's just a point, which is 0 dimensional. But as long as c is positive, then I'm getting an ellipsoid, right? And those would foliate R3, all right? And what that means then is actually there is a distribution of how many vector fields? Too many. What's the role of dimension here? Like, if notice how this works. If the foliation. All right. So what's the dimension? The dimension of this. What's the dimension in my previous example of A? You guys tell me. What's the dimension of sigma c here? Should be k. Yeah. So if this describes like sigma c, right? An integral submanifold of a distribution in R3, we're talking about, the dimension of the distribution being what? Must be 2 here, right? Because this describes a surface in R3, right? Okay, so let's get back to the differential form stuff now that we have a little bit more examples to play with. And let's talk about those. So, lemma, and this is technically lemma 19.5 from John Lee's book. If we have a smooth n-dimensional manifold and we have a distribution rank k on a manifold M which is dimension n, all right, then this is smooth. The distribution is smooth if and only if each P in M has open neighborhood, okay, U, all right, on which there exists smooth one forms, omega 1, omega 2, omega n minus k, such that the distribution at Q is formed by the intersection of the respective kernels of the defining one forms. So we call these omegas, which we were using theta for last time, right? The omegas are playing the role that the thetas were. I'm going to change the notation just a little bit, partly because I don't want to use that stupid circle box thing again. All right, so these are the defining one forms for this distribution, right? on you, all right? This is a local concept, just like we could talk about a set of K vector fields being a local, you know, basis, if you like, for the distribution. Notice that there are n minus k of these, whereas there were k vector. So they're not. It's not the same number, right? They're the sum of the, you know, number, the whatever. If I'm in 4 dimensions, if I've got a 2-dimensional distribution, I've got a 2-dimensional. I have 2 defining 1 forms, but usually they're not the same, right? If I'm in 4 dimensions and I've got a 1-dimensional distribution, I need 3 defining 1 forms. If I've got a 3-dimensional distribution, I need 1 defining 1 form. You know, it should always be dual to the number of defining vector fields. All right. And there's a little bit more I should define. We'd like to define what we mean for a differential form to annihilate the distribution. All right. So, definition. Omega, a P form on M, annihilates the distribution delta if omega of x1 xp is equal to 0 whenever x1 xp through xp are local sections of the distribution. All right. So, of course, the local defining 1 forms annihilate the distribution. It then becomes an interesting question to ask, okay, so what are the local defining 1 forms for my distribution back in example A over here? Right? What are the omegas if those are if my, you know, so over here in this example, what we had was we had x sub I equals to partial xi for I equals 1 to k, right? These are my, you know, smooth local section, right? So what would my defining 1 forms be? I need not k of them, but n minus k of them. Let me remind you, we have from previous work shown that the differential of the ith, let me see, let me use j here. Oh, I don't know. I'll use a and b, why not? dxa of partial b equal to Kronecker delta, ab. No relation to that a. All right. So what should I choose for my local defining forms for this? I need n minus k of them. We just use simply dx, well, let me say j here. dxj for j equals to what? How about k plus 1, n? Those would be my local defining 1 forms. Yeah? No?
Those are the basis for the null space.
Well, the kernel, what's the kernel of dxj, for instance, is the span of partial xi, I not equal to j. Because the only thing that kills are multiples of the jth partial derivative. Everything else, it survives. And so as you take the intersection of all of those at once, you kill off everything except for that which is not touched, namely the first k directions. So like the intersection of these across, anyway. I could write it out, but I don't think it does much if I write it, yep.
So if those terms are not linearly independent at some q, does that mean that that point is not smooth?
If which terms are not linearly independent?
If
These ones? Like if I have two omegas that are linearly dependent?
no, everything else, I think. No, wait, yes, those ones.
I don't know. I mean, these are obviously linearly independent, so that doesn't really give us any insight. I don't know what to say about that, Shane, right offhand.
In that case, partial xi is partial xj, where I doesn't equal j. So then you have degeneracy of your coordinate term.
Yeah, Shane might be, Sam might be right. That might in turn contradict the assumed linear independence of your smooth local section. I mean, we are assuming that the x sub i's are like linearly independent.
Well, I was meaning,
But-
because I think you should have it as you apply it to some q, right?
Well, yeah, I mean, we can adorn this with q. This is true at each q. That's true.
Then you have something like a two directions in the same direction.
But, I mean, this is all to be done, like it says over there, in terms of the point. Yeah. Oh, I'm going to go on. So, sorry, guys. So the next result here, lemma. Same setup. We say eta, an element of the p-forms. So eta being a p-form defined on the open set U annihilates the distribution if and only if eta can be written as the sum I equals 1 to n minus k of omega upper I wedge beta j. I'm sorry, wedge beta I for some smooth p minus 1 forms beta 1 beta n minus k on the open set U that we're talking about. So we can characterize whether or not a p-form is annihilated on the distribution in terms of whether or not you can write the p-form as the wedge product with the smooth, the defining one forms and something else. The proof of that is actually it's a fairly straightforward computation, which I probably don't have time for, but it's essentially just what you do. Although there's an idea in the proof, which we'll probably get back to more next class, which is the idea that if we have this like set of, and maybe this actually goes back to your question a second ago, if we have these defining one forms, right, and we assume that they're linearly independent pointwise as covectors, then we can extend them to a basis of one forms pointwise, right? And it's with respect to that basis that this is investigated. Basically, if, of course, well, over here, right, if you have this, right, and you hit, if you act on a set of p vector fields, smooth local sections of your distribution, of course this is 0 because when the x's get fed to the omegas, they're 0 by assumption, and so if you have 0 into a wedge, it wedges to 0. That's how the wedge product works when you feed it vector fields, right? Because this is, of course, shorthand for some horrible anti-symmetrized tensor product of things. And when you look at the anti-symmetrized tensor product of things, there is an omega I in every single possible one, and that gets fed the distribution vector, the local section, and as such, that goes to 0. So it's pretty clear if we have this form, it will be 0 when we feed it, a p-tuple of smooth vector fields that are in the distribution. The flip side is you extend the basis of the things, and that allows you to write eta in terms of the wedge product of p-fold, the wedge product of p-fold of these and also the other ones that we've extended to. But the thing is, we're assuming that eta works out to 0. And when you study what that means about the expansion with respect to that extended basis, it forces everything to be 0 except these pieces. There always has to be an omega I left over. Everything where there's no omega I in the wedge product of the extended basis, that is automatically 0 because that being 0 forces the things without the omegas to be 0. So what you're left has to have at least one omega in it, and so you can factor it out. And whatever's left over is a p minus 1 form. That's essentially the proof. Yeah. This is very close to Cartan's lemma. Yeah, that's a good question. Is this Cartan's lemma? That is a great question. Is this Cartan's lemma? What was Cartan's lemma? I don't remember either, but yes, it feels like Cartan's lemma. I feel like Cartan's lemma, or I'm saying that weird, Cartan's lemma? I've forgotten how to say Cartan. What's that? Or Cartan? Yeah, okay. I think wasn't it that we had one forms, the wedge of the one forms was 0. It's something about a wedge of forms being 0, and then our ability to write. I don't remember it offhand. I suspect you're right. I suspect that Cartan's lemma is actually a subcase of this, in all likelihood. Oh, I don't want to erase too much here. I think I can erase this. Although I would actually, probably the last example I just erased would not be. I shouldn't have erased it. Oh well. All right. Where's my? Oh, there it is. Whoa. Better get going. So. Theorem. If we have a distribution smooth, then the distribution is involutive. If and only if, and here's we're going to call this whole thing star. So if eta is any smooth one form such that, not such that, one form that, one form? Oh yeah, one form that annihilates sigma. What's sigma? What's sigma? Where'd that come from? The distribution on an open subset. U. Then, guess what? D eta also annihilates the distribution on U. Somebody playing patty cakes upstairs or something? What's that about? Here. What's it? All right.
Star.
I am. Thank you. There we go. So this brings us to a formula I meant to share with you guys a while ago, but I'm kind of glad that I didn't because now we get to see it. So the formula essentially rests, like this whole proof essentially just rests on the following calculation. D eta of x and y turns out that this is equal to, and if this is one of the homeworks that you guys have done that I haven't written a solution yet for, my apologies. But I will catch up with you guys eventually. I'm almost there. I've talked about a bunch of problems I haven't written solutions for, which is very annoying. But I've been a bit distracted. There's been something quasi-political at the university level which has happened, which it's distracting me. So this is just an identity that relates the exterior derivative of a one form and how it acts on vector fields.
I just am remembering this.
Oh, yes.
One of the best days of my semester a year ago has to do with this formula.
Ah. Well, good.
I mean, absolutely serious.
Really? Like,
Is 1438 in John Lee?
I think so, yeah. I think that's probably right. And the flip side of this, well, it's not really a flip side, but if we calculate the smooth defining one form omega I acting on the Lie bracket of x and y, well, so this, if you understand the identity above, we can calculate. You guys, can you tell me what this would be? Like, if this is like a general identity, right? If I look at this one acting on the Lie bracket, see, I just have to basically replace eta with omega upper I and this, and just like work it out, right? So like, put that over there. So I've got, x of omega upper I of y minus y of omega upper I of x, and then of course minus d eta acting on, oh my bad, we're not eta, we're now in omega upper I land of xy. All right.
D omega
I said it, I didn't write, I wrote it, I didn't say it, d omega I, yeah. Where? What? No, this is on purpose. These are different. This is different parts. So like, so let's see here. This is the forward direction. So assume that we have an involutive distribution, right? And then we've got eta as a smooth form that annihilates the distribution. Our goal at the moment is to prove that d eta also annihilates the distribution. It suffices to show it for an arbitrary pair of smooth local sections to the distribution, namely x and y. So why is this 0? Well, we're assuming that eta annihilates the distribution, so this is 0. Eta annihilates the distribution. That's in here. Any one smooth one form that annihilates the, it's part of star. Okay, we don't have to show that. We assume it. So that's 0. That's 0. And
That's the distribution that's involutive.
since it's involutive, this is again in the distribution, and as such, eta kills it. So altogether, 0. Now that only holds on U, right? Where's the U appearing? It's implicit. The domain of the smooth local sections, well, they're local sections. It's only good for an open set. The next one is the other direction. So the other direction, we're assuming star is true. If eta is any smooth one form such that annihilates the distribution on open subset, then d eta also annihilates the distribution on U. That's what we're assuming. We're trying to prove that it's involutive, right? Okay, so what we're doing is we're saying, okay, we're going to let eta equal to omega I and assume star, right? That's where we're coming from. Then we have this identity from just calculus on manifolds. But the thing is that these